All right, great. Yeah, thank you so much. Coming to you here from tropical South Bend, Indiana. I think we're in the 50s today, so it's a wonderfully warm day. And thank you so much to Tessa and Joe Campbell and Mike Withers and Robin and everybody for setting this session up. This has been a blast. I could talk endogeneity all day, and maybe I'm unique in that way, but I love it. So in this particular session, I'm going to cover a little bit about, well, primarily about omitted variable bias, which, like Aaron mentioned and Sarah suggested, is one of 4 sources of endogeneity, but I think it's probably the most pervasive in management research. In fact, we actually did a bit of like a content analysis of publications since 2003. We found that omitted variable bias was discussed in the context of endogeneity almost 11 times more than simultaneity or selection or any other type. So we thought, you know what, maybe we should spend some time focusing a little bit on what's going on with omitted variables and how we can address them. And my camera is like blinking at me. Sorry, hang on one second. I don't know what's happening with it. I'm so sorry. I'm gonna exit this view for 1 second. My camera's like, we're not working. Oh, can you guys see me, or is it gone now?
It's gone now.
It's gone, okay. I think it's, I'm getting like a notification from my USB that it's lost. Okay, I'm just gonna do this no camera if that's okay. Sorry, it's my USB is like, it keeps saying the driver is not found and just keeps flicking out. Of course that would happen right when I'm up, but yeah, sorry about that, guys. But can you see the presentation okay still? Or let me actually share that again.
Yeah, reshare, that'd be great.
Is the presentation up?
Perfect.
Okay,
yes,
good. Sorry, oh man. Yeah, technology. Here at Notre Dame, we're live in classroom, so I don't use my camera all that often. So I'm sure my computer's like, what is this foreign device? So we'll talk about omitted variables, what they are, how they impact models, and then I'm going to talk primarily about a technique that's gaining some traction called the impact threshold of a confounding variable. Sometimes it's called the RIR, robustness of inference to replacement. How we can use that. And how that might guide us in conceptualizing whether or not we actually have omitted variable bias. Let's see if there we go. And so this was created by a guy named Ken Frank in the year 2000. And so instead of kind of just referencing the same papers over and over, I'll just throw the references here. This is basically everything on the ITCV. I was super fortunate recently to publish a book chapter with Ken Frank, and I learned a ton throughout the process. It was with him and some of his co-authors who publish a bit on the topic. And then more recently, as Aaron mentioned, with Mike Withers and Danny Gamache and LU, and we have a paper forthcoming in JOM all about the ITCV and omitted variables. So we're going to build a little bit from that in this presentation as well. At least do some shameless promotion. So in general, this is how omitted variables work. Let's say you were interested in examining the relationship between some characteristic, the independent variable, let's say it's asset complementarity of acquiring and target firms, or some kind of M&A characteristic. And so the outcome variable here is post-acquisition performance. And you might run an OLS regression and you'd get some relationship between those. That becomes problematic though, when there's an omitted variable that is correlated with both of those, just like Aaron was saying, just like Sarah was saying. So here it might be managerial acquisition capabilities, something that we just can't measure. We don't know how good managers are at doing acquisitions, at least without watching them for extended periods of time or surveying them or interviewing them or something like that. And so if that has a non-zero correlation with our independent and our dependent variable, omitted variable bias might exist. And I like to think of this in terms of Ballantine graphics. Kennedy 2008, which is my absolute favorite book, I guess, which shows how big of a nerd I am. But Kennedy 2008, A Guide to Econometrics, loves these Ballantines. So let's think of a dependent. I have these like, I get my daughter these books on physics, like little baby books, quantum physics for babies, which teach me more than her. And it's always like, this is a ball. This is a ball moving through space. So here we are. This is a ball, and it's a dependent variable. And if we envision the circle here as all the variance in that dependent variable, we might be interested in the relationship between an independent and dependent variable. And if we run OLS, we're going to get that overlap between them, that covariance, right? That's what we're interested in finding. What is that covariance? That's going to be our coefficient. That becomes problematic if, so let's call that blue. That becomes problematic if there's also this omitted variable here that also shares a little bit of that overlap and explains some of that covariance. So if we run an OLS regression here, we're going to get blue plus purple as our coefficient, which is inflated, and it's not the relationship between the IV and the DV. It's the relationship between the IV and the DV and whatever is also explained by the omitted variable. So that kind of is the issue here. We want to figure out what's blue absent purple. And so one way scholars do this, exactly like Sarah and Aaron were describing, is with instrumental variables or exclusion restrictions. In my brain, they're one and the same. And that might be this little green section here. And so we're going to find an instrument that explains part of the blue that doesn't overlap with purple. And we'll say, hey, it's good enough. We haven't explained, we've cut out purple with our two-stage instrumental variable model. We're happy with the green. But of course, as we can see here, that green area is not the same size as blue. It would be very unlikely that we can find an instrument that perfectly explains the shared covariance between the independent and the dependent variable. Usually you're just going to get a little sliver of that. And that's called relevance. And then also with your instrument, you're going to get a little sliver of other omitted characteristics. So here we can see where I called it the exogeneity area. So it's explaining some variance that also doesn't overlap with the independent variable. And those are both issues. Both of those together mean that we're not getting a perfect estimate. We're not necessarily getting something that reflects the actual relationship between the IV and the DV. So the question that we were asking ourselves, and that Ken Frank was asking himself 21 years ago now, is what can we do to move away from instrumental variables? Because they're not always perfect, and sometimes they cause more harm than they do good, just like Sarah showed. Simideni, Serto, and Withers, 2014, demonstrate that very clearly as well. Unless we have these perfect instruments that pretty much don't exist in real life, we might have more harm than good in our estimates. And so we thought maybe it would be helpful to focus on the omitted variable itself and figure out what does that actually look like. And so in 2000, Ken Frank introduced this technique, the impact threshold of a confounding variable. And it basically focuses on causal inference or p-values, without saying the word p-values, or a non-zero relationship between the IV and the DV. But it's basically asking, how big would this purple area here have to be in order to explain or to create a non-zero relationship between the independent and the dependent variable that doesn't actually exist, right? So is that purple area so large that it's making your model predict a statistically significant result at whatever p-value you want, or practical level of significance, or however you interpret that? Could be a distribution if you were doing Bayesian models or something, but how big does that purple area have to be? And that's what the ITCV is all about. And so what it essentially does is, if you kind of look, I'm bringing back that graphic there on the bottom of the slide, it essentially says, what would the correlation with R1, the correlation represented by R1 or row 1 and row 2, what values do those have to possess in order to have produced a significant relationship owing to managerial acquisition skills or capabilities is kind of the purpose. And it gives you one value, and that value represents row 1 times row 2, and then you take the square root of that. And that would be the ITCV threshold. And I should say, please feel free at any point to jump in with questions. I do this lecture every year, basically, in my econometric seminar, and we're dealing with the non-existent. We're dealing with the hypothetical and the counterfactual. So it's like we're talking about like something that doesn't exist, and then characteristics of something that doesn't exist by definition because it's omitted. So I understand it's a little bit esoteric. So there are 4 factors that would influence that. In general, a higher ITCV means that an omitted variable would have to have a higher correlation with the independent and the dependent variable to have driven the results. So if you calculate the ITCV, and there are many ways to do that, and I'll describe them here in a second. If you calculate it and it's 0.75 or 0.9, something incredibly high, that means the correlation between the omitted variable and the IV and the DV would have to be 0.75 or 0.9 to have created that relationship. And then, of course, you're left asking, well, what's the likelihood that there's an omitted variable with a correlation that high? And I'll get to that on the next slide. But there are 4 factors that influence this. It's the sample size, it's the estimated coefficient, the estimated standard error, and the level of significance. And all of those, holding the others constant, all of those might increase or decrease the ITCV in general. And the direction of the relationships matters as well. So if you have a positive coefficient in your model, the omitted variable would have to have either a positive relationship with the IV and the DV or a negative relationship with both, but not inverse. And if the coefficient is negative, the inverse would be true. It would have to have an opposing relationship. So if a reviewer ever says, we think you have an omitted variable, we think you might have endogeneity, 95% of the time they're talking about omitted variable bias when they say that. And they might even say, I can think of all sorts of things that would impact both the IV and the DV. All these are fair statements. The question is, can you think of anything that would impact it in these directions, right? We got to make sure that it would have a consistent relationship in terms of the directionality as well. That's one stage to think through. So after you compute the ITCV and it says, hey, it's 0.5, you got to have an omitted variable correlate at 0.5 with the IV and the DV. The next question is, okay, how do we know whether an omitted variable might exist? By definition, we can't measure it. If we could, we would just control for it, but we can't. So what scholars have done is look at control variables and say, hey, we do have all these other covariates. And the first paper to do this in management research was Tim Hubbard, who's in the office right next to mine as we speak. I can hear him talking, and some of his colleagues in 2017. This was the first ITCV paper in strategy, and he'll never let me forget that. But he basically said, look, hey, we have this ITCV value. In order for it to have driven our causal inference, it would have to have a relationship with the IV and the DV as strong as the strongest control variable we have in the model. That seems unlikely, right? If we can control for all these usual suspects, it would be hard to imagine this omitted thing that none of us have ever measured before being as strong as the absolute strongest control variable. And then shortly thereafter, Abby Oliver and myself and Ryan Krause had a paper also in SMJ where we said basically the same thing. Look, the ITCV is 0.25. The strongest control we have is 0.09. So the correlation with the IV and the DV is 0.09. So it's hard to imagine that there's something this large. And almost uniformly, this is how people have interpreted the ITCV. There are a couple caveats with this. The first one is, I think, relatively obvious. Of course, it's possible that there is this omitted construct with such a correlation that does outstrip all of the covariates you have. Of course, the controls are not perfect in terms of explaining. And perhaps, in strategy, sometimes we throw a lot of controls in there just because reviewers ask. I think we did a content analysis on this, and I think the average number is like 23 controls in a model, or just something that's just ludicrous. And the second, and this is something that we discuss in our forthcoming JOM that I hadn't heard yet discussed, and it was actually Ken Frank who clued me into this, is that the ITCV is talking about partial correlations. So if the value you compute is 0.25, that means that an omitted variable would have to be correlated at 0.25 with the independent and the dependent variable after stripping out all shared covariance with all of the other controls. So it would have to be 0.25 above and beyond all of the controls, which, if you compare that to our typical correlation matrix, which is usually zero order, meaning it ignores controls, it's just the raw relationship, it makes it even more unlikely that such an omitted variable would exist. So if we say, hey, look, we have a control with a raw correlation, not including any semi-partial variance with the controls at 0.09, probably the partial correlation there is like 0.009 or something even lower. And you can compute this if you have the data. It's hard to go back and figure out partial correlations just from a matrix, but you can certainly compute it. And so probably the two easiest ways to calculate the ITCV are either in your statistical software program. So you can download an add-on for Stata or SAS or R. It's called Confound with a K instead of a C. And so in Stata, you would just do SSC install Confound. Ken Frank has a website as well. If you Google Ken Frank, Michigan State, there's a website where you can download an Excel workbook as well, where you can just input it'll say, what's your sample size? What's your coefficient? What's your standard error? And you can just input all that and it'll give you the ITCV. Or in our forthcoming JOM and in the book chapter I have with Ken Frank, we just list those resources. You can just kind of copy and paste them into your browser. There's also I should say the ITCV is not appropriate for binary dependent variables and for interactions. And so there's another technique called the robustness of inference to replacement, which I'm just going to gloss over, the RIR, which is computed in the exact same way. But instead of giving you a correlation, it deals with what percentage of your effect size would have to be biased in order for an omitted variable to have driven it. So if your coefficient is 10 and the RIR is 40%, that means that four of the 10 basically, right, would have to have been driven by an omitted variable. Or putting another way is, if you included that variable, would the coefficient drop below 6? Basically, is what it's saying. And so you can kind of add and remove controls from your model and see if it ever drops below 6, kind of just like with the ITCV, to see if there are controls that would impact it in the same way as an omitted variable. So with that in mind, the question that we next asked ourselves was, if we were to apply the ITCV to every published study, we did it in just over a couple of years, but basically in all of the primary management journals, what would the value be and how many relationships might have been biased? And so we threw out everything that was inappropriate and everything that already addressed endogeneity or sample selection bias or did some kind of instrumental variable approach and looked just at the others. And what we found was actually quite revealing. So first, if we interpret if we say, look, if the ITCV value is higher than the 2 strongest controls, we're going to assume that there's potential for an omitted variable to be that strong and to have driven the relationship. And we found that about a quarter of the published studies might have been driven by an omitted variable if that was the case. And on one hand, it's like, oh, that's a little bit concerning. That's kind of high. On the other hand, we would suggest it's actually much lower than we came into this project expecting. So research on the topic, Hamilton and Nickerson is a good example, and Sarah mentioned that. Hamilton and Nickerson basically say, and I love their paper, but they basically say everything we do is driven by omitted variables. There's always omitted variable bias. And then 2014, Samedeni, Withers, and Serto, my absolute favorite paper probably ever published on the topic. They look at all sources of endogeneity, and they basically say, look, if the error term is correlated at all with the independent variable, you got a big problem here. And so you pretty much always have omitted variable, or you pretty much always have issues with endogeneity. And I think for those of you who have submitted papers to journals, I think reviewers run with those, and it's just instantly, nope, you didn't use 2-stage modeling, therefore your estimates are biased. You got an issue here, and we should just go ahead and reject that paper. I think it was Larker and Rusticus have a quote where they're like, look, reviewers, it's like the boogeyman. Reviewers use omitted variables as the reason to reject basically everything, and we're kind of sick of it. This is kind of what they say, Larker and Rusticus, I think, 2010. And so this is actually pointing the other direction. By definition here, you probably don't have an omitted variable problem. And so this is kind of evidenced by, if you look at the number of control variables per study that have correlations that might suggest that the ITCV indicates there's an issue, the median number of controls is 0. So for most studies, there's not a single control variable that has higher correlations with your focal variables than the ITCV value. That's pretty reassuring. In fact, if we were to go back and recompute that 26% figure using the average control variable, so if we assume an omitted variable is as strong as an average control, fewer than 3% of published studies would have been biased by an omitted variable. In my opinion, that's still conservative because these correlation matrices are using 0-order correlations, not partial correlations. So kind of all of these together push us in the direction that maybe it's not an issue. And that's evidenced by the fact that the median ITCV we calculated was about 0.25. So it would have to have, on average-ish, an omitted variable would have to be correlated with the IV and the DV at 0.25. And if we say, okay, well, we can determine whether or not that seems like a realistic correlation by looking at meta-analyses, which is exactly what we did. And so there aren't that many meta-analyses, especially in strategy research, but we went and we looked. The average correlation between strongly theorized variables such that somebody would write and publish a meta-analysis on them, the average correlation was 0.03. So, and that is once again, 0 order. So it would have to be, 8 times stronger than a strongly theorized relationship. And we reason there's probably not a lot of omitted variables out there that would be that impactful, but it's possible. And to that point, and I'm just going to gloss over this table, we actually just ran simulations to this effect. So we kind of replicated Samedeni, Serto, and Withers 2014. In their simulation, they correlated the error term with the independent variable and looked at that. And so what we did was focus exclusively on omitted variables. We generated a dependent variable as a function of X and an omitted variable and an error term. And then in some models, we included that omitted variable in there. And in some models, we just omitted it. And so with these different conditions where it says R equals 0 or R equals 0.1, that's how correlated that omitted variable is with the independent variable. And so when there's no correlation between them, our model predicted, this coefficient here, 0.127. And then in a model where we did not include that omitted variable such that it's omitted, it was predicting something right on those same lines. Then we ran 2SLS with instruments with a couple different strengths and found that it's not as good, right? So you run a two-stage model, the coefficients aren't as accurate, especially when there's no endogeneity here, and they're super inefficient. So if we looked at the standard deviations of those coefficients over 1,000 iterations of simulations, both the potentially biased and the not potentially biased had an identical standard deviation. You start doing 2LS and the standard deviations are dramatic. That means you're more likely to get wildly negative or positive coefficients simply because you featured instruments in your model. But of course, this isn't fair because there was no endogeneity here. There's no correlation between the independent and omitted variables. Then we ramped that up a little bit. What if there was 0.1, which is still a lot higher than we see in strategy research? Same deal. There's not a significant difference between the OLS and the potentially biased model. Depending on the instrument strength, sometimes the coefficient at 2SLS produces is pretty bad, and sometimes it's a little bit close. But once again, extremely wild variance. So you're almost just as likely to get a negative coefficient as you are like an extremely high coefficient with 2SLS. So we ramped that up to the extreme down here. What if there's an omitted variable correlate at 0.4? Which I don't think I've ever even seen a correlation at 0.4, except for with like variables with itself lagged over time. In strategy, I'm sure in OB, that's like a minuscule correlation, but at least in strategy research. And once again, there's a little bit of bias here with the potentially biased model where we throw out that omitted variable. There's a lot of bias if you do 2SLS and the instruments are only correlated at 0.05 with the IV. And once again, there's also a lot of efficiency loss, high variance in the potential outcomes. So what does this mean? Taking it all together, trying to summarize it. Instrumental variable regression is great. It's the gold standard, but it's very hard to implement in practice. So we would like to encourage authors, but mainly reviewers and editors, before levying like the boogeyman of you have omitted variables, we agree that we have omitted variables. Let's think about what they are, though. Are they likely a problem, right? We agree they exist, but are they an issue? And one way we can determine whether or not they might be an issue is with the ITCV. Of course, just like Aaron said, I would, and I think we wrote this, I think I wrote a line of, someone wrote a line of this in one of the papers is, just because the ITCV is really high, sufficiently high, doesn't mean that there is no omitted variable bias. It just means that it's less likely. So it would be untenable to say there is no bias in our model. And the other thing that's important to point out is this deals with causal inference. So it deals with whether or not your non-zero relationship is driven by an omitted variable. But of course, there's a range of coefficients there. So if you're very interested in kind of the practical outcome or the precise accuracy of the coefficient itself, the ITCV is not really that helpful at all. The RIR might be because it gives you kind of like the percent that the coefficient would have to move, but not the ITCV. So with that, I thank you so much, and I'm happy to answer any questions. And I'm going to see if I can turn my camera back on, but I don't think it's going to work. So thanks again.
Thank you, John. Are there any questions for John? We'll kind of open it up to the field to start with.
I just wonder how established this method is. So would reviewers feel overwhelmed when they see it, or are there still some references out there that create some acceptance because your paper is in press right now? So we can't cite it yet, but let's see if it helps once it's out.
Yeah, it's a really good question. And, obviously I don't know how many reviewers have seen it, but in my own reviewing, I have seen other reviewers bring it up increasingly more often. Because I think there are about a dozen papers now published in management journals that use the ITCV. So there's, at least not that I know of, not yet a paper, except the one forthcoming, that describes how to use it necessarily, but several practitioners who have applied it.
I'm really interested in, you touched on it a little bit, control variables, and I'm really interested in your thoughts on, as we look to set up our like, what are your best practices for finding controls? Obviously, you look at previous studies, but what would your recommendations be in terms of kind of setting up controls in your study?
Yeah, that's a good, so maybe I'll start. I would point to, there are a couple of good papers on this topic and that I like to cite at least. One is by Spector and Brannick, and one is by Carlson and Wu, and I don't remember the years. They're both 2010-ish, if I remember. If Mike Withers is here, he might know. He's big on those papers as well. But they both talk about best practices in finding controls and how many to use, how many not to use. I think Aaron mentioned this quickly as a throwaway comment, but I think it's so important. And controls can actually also cause more issues than they solve if they are themselves endogenous. So we love to throw in like firm size as a control. It's like, yeah, firm size causes everything, right? But everything else also causes firm size. And so if assets is correlated with whatever your independent variable is, that might actually be compounding the problem, right? Because there might be a bunch of omitted variables out there that are driving both. So yeah, I wish I could. My recommendation is always just whatever the reviewers tell me to control is what I throw into the model, whether or not I agree with it. But I like to start low and then expand once they ask me.
Thank you.
By the way, is my video back on now? Oh,
Yes,
okay.
we can see you perfect.
All right.
So John, would you recommend presenting this as a justification for perhaps maybe why you don't use instruments if a reviewer is asking for an instrumental variable, or would you just present this from the get-go just to kind of help people structure?
It's a good question, and I'm probably a bad person to ask because my method sections are like 70 pages when I write them, because I'm just going to do everything. But yeah, so I like to present it from the get-go. I like to both use instruments and then explain why I don't think I need them at the same time. And the reason why is because if reviewers love to point out that you have an omitted variable, they super love to point out that your instruments are bad. So like I don't think I've ever submitted a paper with instruments that, I mean, I like them. I wouldn't submit it if I didn't like my instruments. I don't think I've ever done it where the reviewers weren't like, that instrument violates the exclusion restriction. I was like, if I hear that phrase one more time, I'm going to jump out of my window. Which is why I was like, let's find a way to get away from that. And so then I'll say, look, they might violate the exclusion restriction. Here's the ITCV. They probably don't matter anyway. So based on this ITCV. And in our JOM, we talk about, just like Sarah, actually Sarah had some good references. We talk about ways to generate instruments such that they are exogenous. And there's a great technique. I love it. I've used it twice recently, that Lewbel, Lewbel, Lewbel created about using heteroscedasticity in a first stage model to simulate instruments. And so I used that recently in an SMJ that's in late rounds. And one of the reviewers was like, can you just write like a whole appendix on that technique? And then people can cite this paper. Yes, I would love to write. That's great. It's like a free methods paper on a regular paper. So we'll see how that goes.
Great, thank you, John. Does anyone else have any questions on John's presentation? John, again, you left him speechless. We're 3 for 3 here.
Thanks so much, everybody. And sorry again about the video. We'll see what happens going forward, but thank you.
No worries, that's fantastic. Does anyone have any final questions for any of our panelists before we wrap this up? I don't think I see any questions, so I think we are good. I think all of you guys made some wonderful points and offered some really great advice on how to deal with endogeneity, how to respond to reviewers, and really develop the method section of a paper. I think some of the key takeaways that I heard overlapping from everyone are the fact that we want to increase our transparency. So it's incredibly important to think about endogeneity from the get-go and understand diagnosing the problem, do thought experiments to see exactly where the endogeneity may be coming from, and just being transparent and addressing those head on when you are developing your paper. That goes a long way with earning credibility with reviewers and with other scholars in your community. So overall, it's the totality of evidence that we provide as authors that can give everyone confidence in our results. So thank you, everyone. Thank you very much to John. Thank you, Aaron, Thank you, Sarah, and a special thank you to our organizers, Mike and Johanna again. Thank you, participants. We appreciated your wonderful questions.
And I want to thank you, Tess, as well, for a great job moderating this session as well. So thank you. And thank you again to our panelists. I want to echo Tessa's point.